So there are two types of chemical bonds. There are ionic. So these are the two types. You have ionic bonds and covalent. So ionic bonds are formed between compounds that are ionic. It is between compound or elements that are ionic. Ionic bonds form between compounds or elements that are ionic. Okay? So, in other words, you have a metal, which is a cation, right? Metals form cations, positively charged ions, and a, what do you think? Non-metal. So to form an ionic compound, you need a metal and you need a non-metal. With very few exceptions. There's just very few exceptions that we'll learn about, but 98% of all ionic compounds are a metal and a non-metal. Okay? So these metals lose electrons, so they become positively charged. Okay? And the non-metals gain electrons. Those electrons that the metal lost, the non-metal will gain, right? And then they will attract, just like two magnets that attract one another. That's what they're doing. They're attracting because of opposite charge. The opposite charges attract one another. Okay? And then they will essentially stick together. And then they start to form what we call salts and crystals, like salt crystals, because all the positive charges start being surrounded by the negative parts, and you start forming these big crystalline structures. Okay? And so that's an ionic compound. That's what an ionic compound would be. So if I had sodium plus Cl minus, they would form sodium chloride. Okay? They would come together and they would form sodium chloride. That's how we write the formula. But in reality, you don't have just a single sodium and a single chlorine. It's like hundreds or thousands of sodiums and hundreds or thousands of chlorines all put together into a crystal. Okay? So we write the formula like that to represent it, but what it's not representing is how many of those are actually together. Okay? And it'll vary between every crystal. Every crystal is going to have a different number. But that's how we write it, and we call that its empirical formula. Empirical formula meaning the lowest ratio formula. Ionic compounds are written in their empirical formulas.
Lowest what?
Lowest ratio formula. So if I have 100 sodiums and 100 chlorines, then its lowest ratio is 1:1, right? So it's sodium chloride instead of sodium 100, chlorine 100. Okay? So we write it in its empirical formula if it's ionic. That's how it's best represented. Covalent compounds are different. Covalent compounds are different because these are formed between nonmetal plus nonmetal. Now there are very few nonmetals on the periodic table, right? But there are a lot of covalent compounds. There's a lot of combinations that can be created from those nonmetals. And that's how we form covalent compounds. Okay? So ionic compounds are attracted because of opposite charges, right? Opposite charges attract. Covalent compounds are formed because we share electrons. And we create what's called a chemical bond, a covalent bond.
You shared what?
Electrons. Sharing of electrons forms covalent bonds. So if hydrogen has one electron, that's free, a free electron, and oxygen has a free electron, they can share those free electrons to pair. They can pair those free electrons together and form what's called a covalent bond. And covalent bonds will then attract those two things together. Okay? Alright, so these are the two types of bonds that we're going to discuss when we're talking about bonding. Now when we're looking at these, we often use Lewis symbols to portray ionic compounds. Okay? What it's doing is it's showing the valence electrons, because bonding occurs only on the valence electrons. It does not happen on any of the electrons inside. So if we think about the Bohr atom model, all those electrons on the inside are not participating in the chemical bonding. It's only the valence electrons. If I am magnesium, I have how many valence electrons? Number 12. I have 2. What am I going to do with those? I'm going to lose them. I'm going to give them away. Okay? So I'm going to lose the 2 valence electrons. That's where my chemistry happens. It happens on the outer shell. Okay? All those electrons inside, they just stay where they are. They don't participate in the chemical bonding. So when we draw a Lewis symbol for magnesium, we say magnesium and we put 2 dots, and that's magnesium. And it becomes magnesium 2+. This would be the Lewis symbol of magnesium 2+, because it lost 2 electrons. In reality, how many valence electrons does magnesium have now that it lost 2? Where did it go? It went from number 12 to number 10. Now it has 8. Yeah, somebody said it. It has 8 valence electrons, just like neon. Okay? But we don't represent those 8 because we just want to show that it lost 2. It lost 2 electrons. So this would be the Lewis symbols for magnesium. Now for oxygen, if I was going to draw the Lewis symbol of oxygen, how many valence electrons would I put around it? 6. 1, 2, 3, 4, 5, 6. Okay? 2 unpaired electrons, 2 pairs that are paired. We call these right here, these pairs of electrons, we call those lone pairs. Okay? So oxygen is going to try to find something to share these 2 electrons with, right? So it's either going to pick up 2 electrons like magnesium lost 2, so then oxygen could gain them. If oxygen gains 2 electrons, what does it become? What? Oh, yes. 2 minus. What would its Lewis symbol look like if I had gained 2 electrons? Now it has 8 valence electrons. Okay? So that's why we distinguish these 2. When it's a positive charge, we just show what was lost, nothing around it. When it's a negative charge, we actually show all 8, that it now has all 8. Okay? So this would be its Lewis symbol as an ion. Okay, so oxygen, because it's a nonmetal, can either gain electrons and become an ion, or it could start to share this electron with something else and form a covalent bond. Okay? It could form a covalent bond in that one. And we'll look at that in a minute. Okay, so here are, hard to see, the Lewis symbols for different elements. You can see that this first group all has just one dot around it because they only have one valence electron. These guys, and I don't like how they drew it here because they're showing electrons unpaired. Wouldn't do that. Okay? It has a pair of electrons on each of these, 2 electrons, because there are 2 valence electrons here. Okay? 3 valence electrons, 4, 5, 6, 7, 8. So those would be the Lewis symbols for those elements. Simply showing the valence electrons on all of them. They don't show the valence electrons here because valence electrons are a little trickier here. Okay? And you guys don't need to learn how those work. Okay, so we said there's 2 types, ionic bonds and covalent bonds. Okay? The ionics form attractions due to opposite charges. Here, attractive forces due to the sharing of electrons for covalent bonds. Okay. This is all beyond us now, or behind us now. We've already learned all this, right? So sodium has an electron. It loses an electron, becomes sodium plus. Chlorine has 7 electrons, wants to gain 1, then it has 8. So like we said, this is the Lewis symbol for sodium plus. This is the Lewis symbol for chlorine minus, because it gains now 1 electron and it has 8 around it. Okay, now, ionization energy, that's what IE is standing for there, okay? And EA is electron affinity, okay? So atoms with low ionization energy and low electron affinity tend to form positive ions. So we can see that. Who has high electron affinity on the periodic table? Where do we start? Fluorine. Fluorine has high electron affinity, has high ionization energy. As I move away from fluorine, what happens to that energy? It decreases. So as I move to this side of the periodic table, what would we say about these guys and their ionization energy? Low. These guys have low ionization energy. Okay? So atoms with low ionization energy tend to form positive ions. That's what we expect from the metals, that they would form positive ions. Now, ionization energy is the energy to remove electrons. Okay? So those guys, they're not holding on to their electrons very well, so it's easy to remove those electrons. They have low ionization energy. Now, like I said, when we write, so when these things come together, we say sodium and chlorine come together to form sodium chloride. All right? However, it's not just a single sodium and a single chlorine, right? They form crystals like this, these salts. We say they're salt crystals. So you can see there's a bunch of sodiums and a bunch of chlorines in this crystal. But the ratio is what is important. The ratio is 1 sodium for every 1 chlorine. Okay? That's what's important. And so that's how we represent it. We say it's NaCl because for every sodium there is 1 chlorine. So instead of saying 50 sodiums, 50 chlorines, right? And not salt. We want to be able to represent it in its lowest ratio, 1:1. Sodium chloride. That's how they come together. Okay? So all of the salts that we form are all going to form these crystalline structures for the most part. Okay? And we will always write them in their lowest ratio form. Because there's actually no way to predict in the other form. because all the crystals could form different combinations or have different amounts of each thing. Okay, now covalent bonding. So let's look at hydrogen and hydrogen. So hydrogen plus hydrogen forms H2. If we were looking at that in the form of ionic bonding, we would say one of the hydrogens lost an electron and the other one gained it. And we have H plus and H minus. And then they would come together and form H2. Okay? However, both hydrogens have an equal tendency to gain or lose electrons. So they don't actually do that. They don't actually do this. Right? Because they both have a tendency. So who's going to strip the electron from the other guy? That's the question. Is this one going to take the electron or is this one going to take the electron? And the answer to that is neither of those will happen. We don't form an ionic compound here. Okay? Because they both have the same strength for pulling electrons and giving them up. So we don't actually lose electrons. Instead, we share the electron. So this hydrogen has one electron. It wants another one. All it has on its valence shell is an S, right? It has an S subenergy shell. And how many electrons do we need to fill the S subenergy shell? 2. We need 2 electrons. So once hydrogen has 2 electrons here, he will be happy. So to satisfy that, finds another hydrogen who has just 1 electron also. Both are unhappy. And they decide to share that electron with each other. So the electron here is now orbiting both hydrogens, and the electron here is now orbiting both electrons, or hydrogens. Okay? And then they create what's called a covalent bond. Now they are sharing that pair, and it is a covalent bond. So neither one of them gave up the electron. Neither one of them gained the electron. They are sharing it. That electron is orbiting both molecules. Okay? It is orbiting both. And that's what we call a covalent bond.
But is the very thing having to do with the different atoms of the same element? Like, there's 2 atoms and they're both the same element. They both have a
Whenever it's the same, just like this case, so if it was oxygen and oxygen, okay? If it was oxygen and oxygen, then yes, the same thing would happen. Because oxygen has 2 free electrons on it, and if it finds another oxygen with 2 free electrons, they will share those and satisfy both of those empty spaces, okay, with the other oxygen electron. So you would have O2. The stuff we breathe is not just oxygen, it's O2, right? That's how we see it written, as O2. That's the oxygen in the air. That's how oxygen exists, as a diatomic molecule, okay? Same thing with fluorine and nitrogen, okay? F2, N2. That's how these elements exist, all right, in the air, or as gases. That's how they would exist, because of this, because they're sharing those electrons, okay, perfectly. So here you can see it through the electron cloud, okay? We have 1 free electron here, 1 free electron here, and that E is just representing that this whole blue area is a cloud of electrons. Okay? And as they are moving closer, these 2 nuclei, the protons here, are moving closer to one another. You can see now these 2 electrons are not distinguished by just 1 nuclei. They will surround both nuclei and orbit both. Okay? And now we have created a covalent bond and a covalent molecule. So here's an example of fluorine. Well, here's an example of a bunch of them that do that, right? H2, N2, O2, F2, Cl2, Br2, I2. this is going to be important for you guys to understand, because sometimes you are given questions that ask you to write out the chemical formula. And if it says something like, you react hydrogen with oxygen to form water, or even if they told you water was H2O, okay, you would need to understand that the correct formula would not be hydrogen plus oxygen forms H2O. What would be, this is incorrect, how would I correctly write that?
H2.
H2 plus,
Would you put the 1?
what did we say about oxygen? O2 yields H2O. And because when we start talking about balancing chemical reactions, this one up here will balance differently than this one. Here I would need 2 hydrogens over here and it would be balanced. 2 hydrogens there, 2 hydrogens there, 1 oxygen, 1 oxygen. Here it's not the same thing, but this is the correct formula. Okay? So I would need 2 oxygens, so that means I would change this to a 2 to have 2 oxygens on both sides, and then H2, but then times 2, so I need 4 hydrogens over here. 2 times 2, 2 times 2. Now it's a balanced chemical equation. So if I balance that one, it would be wrong. If I balance this one, it's correct. Okay? So you need to understand that when we're talking about these elements, such as these ones right here, okay, you need to make sure you're using them in their diatomic form in the chemical formula, or else it'll be, it'll give you incorrect information. It has to be in its diatomic form. Okay. Now, in the end, when you have a covalent compound, one thing that you have to be sure of is that everything has 8 electrons around it. Okay, so let's count how many electrons are around this first fluorine. 1, 2, 3, 4, 5, 6, 7, 8. Now let's count how many electrons are around the second fluorine. 1, 2, 3, 4, 5, 6, 7, 8. Did you notice I counted these twice, both for this one and for this one? Okay? So when you're counting the electrons in a covalent structure, which you'll be doing in just a little while, you need to make sure that these ones are counted for 8 on both. Okay? Because I can see now that these electrons are both surrounding this fluorine, so it has 8, and they are surrounding this fluorine, so it has 8, and they are forming a covalent bond.
So in an element, like it has one that is alone, pair.
Right here?
It can go with another one alone, with one can go
And form a pair.
That's why you did them together.
That's right. That's why. So for example, oxygen, okay, has 2 lone electrons, okay, and it could form bonds with another oxygen because it would share, these 2 would share, and then these 2 would share. And then you would form okay, so those 2 electrons are being shared by both of them. Whoops, that wasn't completely accurate because you have 2 pairs that are being shared. Okay? Okay, that's really off. Okay? What's that?
It's difficult that in the joint because it's bigger, so in the middle will be 4.
Okay. So these two pairs are being shared by both oxygens. Okay? I heard enough.
So you're not just
in that case you are, because you had an electron here and an electron here that both needed a partner, right? And so they form those partners, okay, with both of them. So now these 4 electrons are being shared by both oxygens. And they're forming what we say 2 covalent bonds. So in other words, fluorine that shares just 1 pair of electrons would have a single bond. Oxygen shares 2 pairs of electrons, and it has a double bond. Okay? So if I'm counting electrons, because this is how you're normally going to see these bonds, as lines. This is a bond. That bond represents how many electrons? 2. So I have 1, 2, 3, 4, 5, 6, 7, 8 electrons on this fluorine. I have 1, 2, 3, 4, 5, 6, 7, 8 electrons on this fluorine as well. Here, oxygen, 1, 2, 3, 4, 5, 6, 7, 8 electrons on this oxygen. 1, 2, 3, 4, 5, 6, 7, 8 electrons on this oxygen. That's how I count the electrons. Yes?
Sounds like the 2 electrons that are alone, and since there's not 8, that's why those last 2 are alone.
These ones? Is that what you mean by the last 2?
Because those are...
These electrons?
Yeah, so like, because there is only 6, like, that's why I had to have the bonds for 6, and that's why those 2 weren't up there.
That's right. Yeah. There was only 6. We wanted 8. So we need to get 2 extra electrons from somewhere. Well, oxygen found another oxygen who also had 2 electrons who weren't paired. And they pair both of those, and they form covalent bonds. And now each of them have 8 electrons orbiting their nucleus. Okay? And those are what we call the covalent bonds. Yeah. Okay, any more questions on this? Okay, so here is another example of some covalent bonding. Okay, if you have an oxygen, like we said, it has 2 free electrons, right, that aren't paired. Hydrogen has 1 free electron each. So if we take 2 hydrogens and we react it to this oxygen, then that oxygen will then share those free electrons with the hydrogens, and it will form 2 covalent bonds. So here we have satisfied both hydrogen and oxygen. Hydrogen wanted 2 electrons, it only had 1. Oxygen wants 8, it only has 6. So we take those 2 hydrogens, put them on there, and we form water, H2O. Carbon has 4 valence electrons, right? So it has essentially 4 free spaces for bonding. 1, 2, 3, 4, right? So I take these hydrogens and I can pair a hydrogen with each of these electrons that need a pair, and I form CH4. So this is H2O, this is CH4. And it is bonded covalently to each of those hydrogens. So in this structure right here, I'm going to count the electrons around this carbon. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons around that carbon. How many electrons are on this hydrogen? 2. Each line represents 2. 1, 2, because these 2 electrons are being shared by hydrogen and by carbon. So carbon has 1, 2, 3, 4, 5, 6, 7, 8, and hydrogen has 2. Hydrogen's happy, carbon's happy, and they're both happy. Okay? So they have formed that covalent structure in that manner. Okay. Now, most of the things we've looked at so far, we would classify as being non-polar molecules, and we'll explain that in a minute. But there are also things that are called polar covalent molecules. Okay? And a polar covalent molecule is one that is created from an unequal sharing of electrons. So in other words, somebody is a little more greedy than the other one. Okay? So here we have hydrogen and fluorine. They bond together covalently, H and S. And you can see that hydrogen has 2 electrons, fluorine has 2 electrons. Now, fluorine is the most electronegative element, meaning it pulls electrons stronger than any of these other guys. So because it's the most electronegative and it pulls electrons towards itself, when it bonds with hydrogen, who is not as electronegative as fluorine, then what happens is those electrons that are supposed to be around both of them, they will orbit fluorine. So here we have an HF bond. These electrons are going to orbit fluorine, and they go around hydrogen every once in a while. You guys can't see that. They're going to go here, and then every once in a while they go over here. More over here, and then every once in a while over here. Okay? So even though they're still sharing them, fluorine is sharing them more. Okay, he's the older brother that doesn't share very well. What's that? Fluorine shares them more. He gets them more. Or I guess shares them less with hydrogen. Yeah. He holds on to them for longer, and then he'll give them to hydrogen every once in a while. And what that does is it creates what's called a polar molecule. So, in other words, it gives it what we call polar character, which means fluorine, because the electrons are around it more often, becomes partially negative, and we write that little lowercase delta symbol for partially negative, and hydrogen will be partially positive. Okay? Because fluorine is pulling that negative character towards himself. Those electrons are more around fluorine than around the hydrogen. It's not really an S, it's a delta, lowercase delta. Kind of a squiggly circle at the bottom. So I guess kind of an S with a closed off down at the bottom. Okay, so partially positive and partially negative for hydrogen and fluorine. Water is the same way. Oxygen is right next to fluorine, so oxygen is also very electronegative. And when it bonds to hydrogen, oxygen takes the electrons more, holds on to them longer. And so you create that same kind of situation. Okay? Where the electrons are more around oxygen, so it's partially negative because the electrons are around oxygen more often, and the hydrogens both become partially positive. Okay? And it's a polar molecule because it has polar ends to it. Positive and negative ends. Okay? Because of unequal sharing. So here they're showing fluorine and hydrogen. This fluorine is partially negative. This hydrogen is partially positive because of the unequal sharing of the electrons. But it is still a polar molecule because they are still sharing electrons. They didn't lose the electron completely and the other one gained it. Okay? That would mean it's ionic. HF here is actually starting to become ionic. If it was any closer, if the electronegativity differences between fluorine and hydrogen were any greater, if the difference is in that, then all of a sudden it would become an ionic compound. It would just, fluorine would steal that electron. But hydrogen has enough pull on its electron that it holds on to it well enough that it keeps it in the covalent realm. Okay? But these metals, they don't have the pull. They can't hold on to it. Lithium's going to lose its electron. Sodium's going to lose its electron. It's going to lose the electron, and fluorine will grab it and hold on to it. And it will become an ionic compound instead of a covalent compound. Okay? So, electronegativity, I'm not sure why they threw this one in here after polar, but so here you can see the differences in electronegativities between a lot of the molecules. Fluorine, 4.0. Okay? You can see that's the highest electronegativity on the entire periodic table. As you move away from fluorine, you'll notice the electronegativities are decreasing. Okay? But these nonmetals have the highest electronegativities. 4, 3, 3.5, 3, 2.5, 2.1. Okay? These guys are all in the electronegative realm. And then as you go to these metals, they don't have high electronegativity. And so those electronegative molecules will steal the electrons from these metals. They will just steal it from them because they can't hold on to it very well. And that's why they're a metal. They don't hold on to their electrons very strongly. Okay? Hydrogen is not a metal. Don't let that confuse you. Even though it's on this side of the periodic table, it has an electronegativity of 2.1. It fits more over in this realm. Okay? With these guys, forming covalent compounds. And not really ionic ones. Right? So, just briefly, this is how they determine the larger the difference in electronegativity, the more ionic character you have. So, H&F, 4.1 to 2.1, 1.9, it's a more ionic character than HCl, which is 3 to 2 minus 2.1, which is only 0.9. Okay, so this is a more covalent molecule than this one. This one's reaching over into the realm of becoming ionic because its electronegativity difference is starting to become larger and larger. Sure. So if we go back to this chart, fluorine has electronegativity of 4, hydrogen of 2.1. So 4 minus 2.1 shows us the difference in electronegativity between those two. Okay? So if I look at the electronegativity between fluorine and lithium, it's 4 and 1. So that's a difference of 3. Okay? So because it has such a large electronegativity difference, it becomes an ionic compound. So electronegativity of 3 would then throw it into the ionic realm. Okay? Over this is still covalent. Barely. HF is barely covalent. Okay? And also the HF bond is more polar than the HCl bond. Okay, now for the real fun stuff. Naming covalent compounds and ionic compounds. So we call this nomenclature. Okay, we say this is nomenclature. So nomenclature is assigning a name to compounds. And we create a system of naming that is the same between all scientists. Okay? And we call that IUPAC, the international system. Okay? Now there's two naming systems, ionic and covalent. So we name each of them different because the compounds are different. And in ionic compounds, when we write the formula, we just write their lowest ratio. We don't write how many there are. But in covalent compounds, we have to state how many of each thing, how many oxygen, how many fluorine, how many carbons are there. Okay, because that is important. For example, CH4, C3H6, C6H6. Okay, so these are all covalent, all three of those. But I can't just say, I can't name it as carbon and hydrogen, because that wouldn't tell me that these three things are different compounds. But ionic compounds, they only take one ratio between each element. So if it's magnesium and oxygen, there's only one ratio between the magnesium and the oxygen. So I name that differently than I name these carbon-hydrogen elements. Okay? Covalent, ionic. With ionics, we just have to know which elements we're dealing with, then we can find the name. With covalence, we have to know how many of each element we have in the compound before we can name it. Okay, so these chemical formulas, we've already kind of seen use the subscript as how many you have. So within a compound, here this is showing me that I have 6 carbons, 12 hydrogens, 6 oxygens. Okay? This is a covalent compound. So this is glucose. Okay, that's a common name for it. We're actually not going to learn how to name this structure. We'll learn how to name binary things, just 2 elements, okay, not 3 like this. But glucose here has a structure like this. Oxygen bonded to a carbon, another carbon, 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 carbon. And then carbon up here. Okay, so this is a sugar molecule, the stuff you eat. Okay, and because of the structure, it tastes sweet in your mouth. Okay, the chemical structure causes it to taste sweet. Your brain perceives it as such. So if I counted up all the carbons, I would have 6. All the hydrogens, I would have 12. All the oxygens, I would have another 6 oxygens. And that's how I get to this chemical formula of C6H12O6. Okay, but you can see this is covalent. I'm sharing all this. None of this is ionic. Okay? Ionic compounds form the crystalline structures, and we can't represent them as how many of each thing we have. We have to represent it as its individual ratios. What are the empirical formulas? What would be the empirical formula of this, by the way? Close. CH2O. Sugars are called carbohydrates, carbon waters, carbon H2O, CH2O, because all sugar molecules have that empirical formula. They have that empirical formula, CH2O. So that's why they call them carbohydrates. Okay? So if I was given the empirical formula of this, I wouldn't know, I wouldn't be able to name it, because I can't go back to there without more information. Okay? So I cannot write the empirical formula of a covalent compound. I have to write it in its molecular form to represent it correctly. Okay? So empirical formulas are written for ionic compounds. Covalent compounds, I have to write them in their molecular form as their formula. Okay? Because this thing just is a big molecule that's just all stuck together. It doesn't come apart. It's not ionic. It just remains as it is like this. Okay? So, ionic compounds. Metals and nonmetals, right? We need a cation and an anion. We need something that loses electrons and something that gains them. So we can form ionic compounds. The metals are the cations, the nonmetals are the anions. They arrange themselves in three-dimensional repeating crystal lattices, so we can't decide how many of each thing we have. We represent them in their lowest ratio formula. Smallest whole number ratio. That's how we write it. Okay? So, to determine the name of an ionic compound, or maybe to go back to what is the formula of an ionic compound, we first need to determine the charge of the ion. Okay? So, let's say we're talking about sodium and nitrogen. What is their formula, their chemical formula, going to be? What is the charge? First thing I have to do is I have to determine what the charge is. Sodium has what charge on it? +1. It's a metal. It will lose electrons. It will become +1. Na+. Nitrogen, 3-. So now the question is, how many sodiums and how many nitrogens do I need to form this compound so that their charges will equal 0? The compound, the charges need to equal 0. 3 what? Okay, Na3, 1 nitrogen.
How'd you get the 3 for that?
For sodium? I have 1 positive charge there, so I need how many sodiums to balance out this negative charge?
How did you know that was a 3 for that?
Oh, okay. Nitrogen has how many valence electrons?
5.
5. Okay. I need how many? 3 more to get to 8.
Okay.
Okay, I have 5 valence electrons. I need 3 more to become 8. All right. So the nonmetals, I can predict their charges. The first 2 columns of the periodic table, I can predict their charges. +1, +2. Okay? We're going to look at in just a minute what we're going to do about these guys in the middle. Okay? Because they're all over the place. All right. So Na3N. This is the formula for this compound. It would never be anything else but that. Okay? That's the empirical formula. That's the formula of it. Na3N. So, you don't have to tell me that there are 3 sodiums here in the name. I don't need to know that. Because I know that whenever it says sodium-nitrogen compound, it's ionic, I know that I'm going to have how many sodiums? How many nitrogens? 1. Okay? So the name of that would be sodium, whoops, how am I writing it? Sodium nitride. Sodium nitride. Okay? I know that it's a sodium and nitrogen compound because of the name. Na-N. I know this is +1 and this is 3-. So I know the formula must be Na3N. This is what you're going to want to do, which you cannot do. You're going to want to tell me there are 3 sodiums there. You're going to want to say trisodium. No, no, no. It is an ionic compound. I don't have to say how many there are. Trisodium is wrong. Trisodium nitride would be wrong. All you have to say is sodium nitride. From that name, I can get to here. From that name. Okay? Magnesium phosphide. What is its chemical formula? Phosphide. Magnesium phosphide. What is its formula? You're right. Okay? What is its formula? Let's start with identifying the covalent, or sorry, the valence electrons, one of those things. The valence electrons on magnesium. Okay, so what kind of ion will it become? Cation. Positive 2. Thank you. Mg2 plus. Phosphide. Good. What is the chemical formula? Now, remember, just switch the charges to subscripts. If I have Mg2 plus, that means I need how many phosphorus? If I have phosphorus 3 minus, I need 3 magnesiums. Mg3P2. Just switch the charges. That's it. Now I know the chemical formula for magnesium phosphide. Nobody had to tell me try magnesium diphosphide. They didn't have to tell me that. Because all I have to do is switch the charges. Okay? If you write trimagnesium diphosphide, that is going to indicate that this is a covalent compound, and it is not. It's not negative anymore because I balanced the charges by bringing in 3 magnesium 2 pluses and 2 P3 minuses. Okay, I brought those together and they balance out their charges to 0. So 3 magnesium 2 pluses would give me a charge of 6 plus overall. Because each one has a 2 positive charge. Having 3 of them, I get 6 positive charges, right? Phosphorus has 3 negative charges, but I have 2 of them. 2 times 3, that's 6 minus. They balance. So it's 0. Okay? But I need that many of each one of them to balance it. Okay. So we're going to predict the formulas for these compounds. Sodium and oxygen. What's the formula? Okay, so I have Na plus. Oxygen is what? O2 minus. So what is the chemical formula? Na2O. Right? 2 minus means that I need 2 sodiums. 1 plus means that I need 1 oxygen. Okay, let's try the next one. Lithium and bromine. Li plus. Bromine is what? Br minus. The formula? 1-to-1, right? Lithium bromide, 1-to-1. Aluminum and oxygen. Now, aluminum is a metal, so it loses electrons, right? How many will it lose? How many valence electrons does it have? 3. It will lose. It has 3. It will lose 3. Okay? It is one of the only things over there in the P group that is predictable in that fashion. Okay? It has 3 valence electrons. It will lose all 3 of its valence electrons. Okay? So it's going to become Al 3+. Okay? Oxygen is what? O2 minus. What's the chemical formula? That's right. Okay? It just takes a little practice. Al3O2. Al2O3, sorry. Okay? Barium and fluorine. Well, barium's number 56. Okay, whoever said that, that's right. Right. 2 positive. Fluorine. No, that's 1 too many. It has 7. It wants 8. It needs 1 more. Okay. It has 7, it wants 8. So the formula, I'm sorry? F minus, because it has 7 valence, it wants 8, just needs 1 electron. So BaF2. And I have my formula. Okay? Good. So that's for those ionic compounds. Now the ending. What is the ending? IDE. That's the ending. Well, it is the ending unless there's another situation that we'll talk about in just a minute. But if you're not one of those other things, you're an IDE. So all these elements all by themselves, they are IDEs if they are a non-metal. Magnesium keeps its name. It's the cation, keeps its name. Magnesium ide. Magnesium nitride. Magnesium oxide. Magnesium fluoride. Magnesium sulfide. Okay? So it is the non-metal that takes the IDE ending of the name. Sodium chloride. Sodium oxide. Lithium sulfide, aluminum bromide, calcium oxide. All right? So the non-metal takes the IDE ending. That's where we put it. Okay. Now, whenever it's a transition metal, we have to consider another aspect, and that is the fact that that transition metal can have multiple charges. It could have +3, +1, +2 if it's iron. So I cannot write the name of iron and chlorine as iron chloride. That's not enough information, because it's not telling me the charge of the iron metal. Okay? So, if it was an iron with just a 1 positive charge, then I would write it Fe plus Cl minus. And my formula would simply be FeCl, right? If it was iron with a 2 positive charge with a chlorine, then I would write it FeCl2. If it was an iron with a 3 positive charge, then it would be Fe3 plus Cl minus. and then it would be FeCl3. Those are all three different compounds that can form. Okay? So, and the difference is simply the charge. It is the charge on the metal, right? That is the only thing that is different. So if you tell me what the charge is on the metal, then I can write the formula. And the way that you tell me the charge on the metal is by putting it in Roman numerals in parentheses. So this compound right here would be named iron 1. What's the charge on the metal? 1 chloride. Okay, finish the name. What's this one called? The charge is 2. Iron 2 chloride. That is enough information now for me to write the formula, because I know if it's iron 2, it's Fe2+. This one is called iron 2 chloride. What's this one called? Okay, now this is not only for iron. It's for cobalt and nickel and copper and manganese and chromium, all those transition metals. It's even for lead and tin over here in the P block. Okay? So metals over here in the P's and in the D's, we have to do this. We have to state what the charge is on the metal to be able to write its name. Okay? What is the name of that? That's a 3 down there on the oxygen. I think you said it. Oh, yeah, because what's the charge on this iron? 3. Fe3+, right? How do I know that? Because that goes right there. Whoa. That goes right there. Iron 3+, oxide O2-, right? And that's how I get to there, Fe2O3. Iron 3 oxide, that's its name. That's how I would name it. Iron 3 oxide. Now, this is the most common mistake. This is how most people name that compound. Iron 2 oxide. Because what did they do? What was the mistake they made? They decided this is what they would put here instead of the charge of the metal. This iron does not have a 2 positive charge, it has a 3 positive charge. So the correct name for this is iron 3 oxide, not iron 2 oxide. Okay? So please be careful of that. Please be careful of that. Don't put 2 there. Polyatomic ions. Okay, that's the next big square on your thing. Okay? So polyatomic ions are ions, that means they have a positive or a negative charge, but they are more than one element. So they are poly, meaning many. So you can see here, I don't have just a nitrogen, I have a nitrogen and 4 hydrogens. Okay? And it is positively charged. This compound is positively charged. It's called the ammonium ion. Okay? So it is a polyatomic ion. So when you name compounds that have polyatomic ions in them, you need to know the name of the ion. SO4 2-. Sulfate. That is the sulfate ion. There is a chart in your book that looks like this. H3O plus, hydronium. NH4 plus, ammonium. NO2 minus, nitrite. NO3 minus, nitrate. Okay? So these are the names of the polyatomic ions. The reason a lot of times you get confused when you're naming things is because you want to name something using a polyatomic ion name when it's not. So for example, if I had something, yes, like magnesium sulfide, okay? You might be tempted to say that is magnesium sulfate. This is not magnesium sulfate. Magnesium sulfate would be this. This is magnesium sulfate. Because sulfate is SO4 2 minus. So Mg2 plus, right? SO4 2 minus, they balance. So magnesium sulfate. Magnesium sulfide, IDE. When it's just the element, it's an IDE ending. When it's a polyatomic ion, I use the name of the ion. SO4 happens to be sulfate. Okay? Now, if we look back at this chart, there's actually a procedure as you reduce the number of hydrogens or oxygens, excuse me, on a lot of these polyatomic ions. So for example, right here, if I go to ClO2 minus, that is chlorate. Nope, sorry, that's chloride. Chlorate is ClO3 minus. ClO3 minus chlorate. If I reduce the number of oxygens from ClO3 to ClO2, I go from the 8 to the ite. And that is the same procedure for any of these 8. So, for example, where are you? PO4, 3 minus, phosphate. If I reduced this to PO3, 3 minus, it would be phosphite. Okay? PO3, 3 minus would be phosphite. PO4, 3 minus is phosphate. So reducing the number of oxygens from the ATE ion makes it go from the 8 to the ite. Okay? Now, if I go even further, like this one, ClO2 minus, going from the ite down to ClO, now it becomes the hypoite, hypochlorite. Okay? Chlorate, chlorite, hypochlorite. Alright, so that's kind of the trend of this. Now, do you have to memorize this chart? No, you don't. It's provided to you on a test. Okay? So if you're going to name something on the test, that chart will be there for your reference. Okay? But I believe on the homework, sometimes you might go from carbonate to carbonite, and carbonite's not on here, right? So you need to realize, what is carbonite? CO2, 2 minus. The charge stays the same. The only thing that changes is the number of oxygens. Okay? So carbonate, carbonite. CO2, 2 minus. Okay? So if you look at this, the chlorate series here, it will show you how it goes. From chlorate, if I go up an oxygen, it goes to perrate, perchlorate. Okay? So ClO3 goes to ClO4. This charge, you'll notice, on all these chlorine oxygen polyatomic ions are all -1. So the charge does not change as you remove or gain oxygen. The name does. Hypochlorite, chlorite, chlorate, perchlorate. But the ATE ion is the reference. That's the reference. Because you'll see this one has 3 oxygens, whereas phosphate has 4. So if I went to PO3, that's phosphite. Phosphite.
So it's still going to be 8 again if you continuously add oxygen. Like for the 3 to the 4, it's still at 8.
What do you mean?
For chlorate, and then chlorate is still 8 instead of I. So if you're
ClO4?
yeah, so if you're
It's
adding
per
to it,
8, per chlorate, instead of chlorine. Now it's per chlorate. Okay? Alright, now, really quick, this isn't going to take long, let me show you how to name, and we'll look at those in a minute. Let's see how we name things that are covalent compounds. Okay? We have to use this. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay? Those are the prefixes. They're just prefixes. They just say exactly how many things you have in the formula. So, for example, PCl3. Phosphorus trichloride. Phosphorus trichloride. CO2. Carbon dioxide. We're still doing ide at the ending. Carbon dioxide. Phosphorus trichloride. Okay? So do you see naming covalent things is not difficult. That's why when you start naming ionic things, you want to name them this way. And you start trying to put prefixes on the name of your ionic compound and you get it wrong. Okay? So, this is real easy. And if you want to look at your paper here, you'll see, okay, a few sections on doing that. So, number 1, SF6. Six is hexa. Exactly. Sulfur hexafluoride. Now, why don't I say monosulfur? It's because the very first element, I don't say mono. Okay? But if it was this, if it was that, then I would say di. Disulfur hexafluoride. Okay? But if it's the first element and there's just one of them, I don't say mono. Okay? But I do use mono in this one. Carbon monoxide. So we're going to learn about how to draw structures. And if you follow closely, there are just a few steps that will make it very easy. Okay? If you follow these procedures and steps, you will be able to draw these structures without any trouble. Okay? So you're given a chemical formula for a covalent compound. And you want to draw the structure of that compound. That's what we're going to learn about. Okay? So this is covalent things that are bonded by sharing electrons. So when we draw their bonds, we draw lines. Okay? Ionic things, they just come together. And we don't really show their structures because they're just crystal lattices. But these are different. They have actual structures to them. Crystal lattices. It is. Okay. So we are going to take, so this is the guidelines. And so I'll go through these quickly and then I will go through it by showing you some examples of how to do it. Okay? So first, you look at the chemical symbols for various elements. Usually it's two things. Okay? The least electronegative atom will be placed in the central position. Hydrogen and halogens occupy terminal positions. So a hydrogen can only make a single bond. That's it. So it could never be in the middle of something, right? Because to be in the middle, you have to at least make two bonds. So hydrogen is always on the outside. It is never in the middle. Fluorine, chlorine, bromide, iodine, those are the halogens. They only have one vacancy, one electron vacancy. So they also only make a single bond. Exactly. Fluorine, chlorine, bromine, iodine. Okay? They won't be in the middle because they only make a single bond. And that's it. Now, we put the least electronegative atom in the central position. Hydrogens and halogens, if they're in your compound, they will go on the outside. Carbon often forms chains. Okay, it's not going to be a big part of what we're doing. Determine the number of valence electrons. So this is part 2. So I draw my I know which one goes in the middle. I determine the number of valence electrons total. Okay, so we're going to see how that works. You connect the central atom to each of the surrounding elements. Okay, you complete the octet. That means every single element has to have 8 electrons on it. If it doesn't, you've done something wrong. Okay, that is going to be an important check for you. If all of a sudden you have 10 electrons on your central element, you know you did something wrong. Okay? If there are not enough valence electrons, move lone pair electrons to terminal atoms to form new bonds. We're going to see how that works. Recheck. Make sure everything still has an octet. Okay. So this is for covalent compounds, obviously. Arrange the atoms in their most probable order. So they're saying you wouldn't go oxygen in the middle surrounded by a carbon and another oxygen. Carbon is going to be the least electronegative. It's going to be in the middle surrounded by the 2 oxygens. And that's going to be, usually it's one thing in the middle surrounded by everything else. Okay, so whatever there is the most of is usually surrounding the thing that goes in the middle. It'll be pretty obvious to you, though, for the most part. Okay? All right. So instead of letting them draw CO2 for us, let's draw it ourselves. So we are going to follow those procedures. CO2, we want to draw the structure of carbon dioxide. Okay? Now the first thing that I usually do is I determine the number of valence electrons. One carbon has how many valence electrons? 4 valence electrons. How do I know that? Periodic table. Look at its position on the periodic table. Okay, it's right under group 4A. That means it has 4 valence electrons. Okay, sometimes on other tables it says 14A. So 4. 4 valence electrons. Another way I know that is if I count S and P electrons. 1, 2, 3, 4. Okay, S, 2 S's, 2 P's. There's 4 valence electrons. The valence electrons are always the S and P electrons. All right. How many valence electrons does oxygen have? 6. It gains 2. There you go. Okay. It has 6 valence electrons. It wants 2, but that we don't care. We're not doing that for this because this is not ionic. It's covalent. So it's going to share electrons. So this oxygen is going to share electrons. Now there are 2 of them, so how many total valence electrons are on these oxygens? Good. So in this structure, my entire structure will have how many total electrons surrounding it? 16 electrons.
Wait a second, can you go back to how you got 12?
Sure. So one oxygen has how many valence electrons? Okay, and I have 2 of them, so 2 times 6, that gives me 12. Okay? So I have 12, I'm sorry? Okay, I just said 12 plus 4, and I got 16. Are you okay now? Or? Okay. All right, so I need 16 total electrons. Does everybody see how I got 16 now? Okay, I just counted how many total valence electrons I had. I had 4 here for carbon. I have 6 for each oxygen, but I have 2 oxygens, so that's 6 times 2 is 12. I add those together and I get 16 electrons, valence electrons. So now I start everything out having 8 valence electrons on it. So I draw a carbon in the middle, surrounded by 2 oxygens, like this. And I want to draw my structure. So I put electrons around so that everything has 8. Each line represents how many electrons? 2. So right now, the first oxygen has 2 electrons on it because of the line. The carbon has how many electrons on it?
4.
Good, it has 4 because it has 2 lines on it. The other oxygen has 1 line, so it has 2. 2 single bonds right now. So I need to add 6 more electrons to the first oxygen to make sure that it has 8. 1, 2, 3, 4, 5, 6. And I'm going to represent the electrons as dots in pairs because electrons pair, right? That's what they do. We call these lone pairs. So this oxygen right here, right now, has 3 lone pairs. So on your homework, when it's asking you questions about the structures and it says how many lone pairs are on the oxygens, right now we see that there are 3 lone pairs on the oxygens. The other oxygen would have the same because everything needs 8. How many lone pairs will I put on the central carbon? No, I need to put some there because it doesn't have 8 electrons in it.
4.
4 more electrons. How many lone pairs? 2 lone pairs. 1, 2 lone pairs for a total of 8 electrons. Okay? So now I have 2 lone pairs on the carbon, 3 lone pairs on each oxygen. So when the question asks how many lone pairs are on the oxygens, you say 3. Not 6, because 6 is total electrons on the oxygens together. That's not what it's asking. Okay? It's asking how many lone pairs are on each individual oxygen. Right now there's 6. Okay? I'm sorry. There are 3. Okay? Here it's not 6. There are 3 lone pairs on each one. Alright. Let's count the total number of electrons right now on this compound. Valence electrons, that is. There are 20. Okay? So for those of you that didn't see how we got that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 electrons on this structure. Okay? Yes? Okay, it had 16 before I added those 4, right? So why? Because everything has to have 8 valence electrons. That is a requirement. Carbon only had 4, so it wasn't satisfied. It wasn't in its real state. But we're going to see how we take care of this situation. Because I have too many electrons, right? How many should I have? 16. So a common mistake people do is, so I'm going to redraw this so you can actually see it. They get to this point and they say, okay, there's 20, I need 16. So I'm just going to remove the electrons on the carbon. But that takes us back to our original situation where we don't have 8 electrons on carbon. Okay? I can't just take away these electrons right here. So what I have to do is, instead of removing electrons, is I need to share electrons. How do I share electrons? By making what? By making bonds. Okay? So, here's my structure. Okay, so to make a bond, I have to share pairs of electrons. So if I add a bond between this carbon and that oxygen, okay, now I have to manipulate both the carbon and the oxygen I added the bond to, because now I have too many electrons on each one. But because I added a bond, that means I added 2 electrons to each thing, which means I can remove 2 electrons or a pair of electrons from each thing. Okay? So, let's see if I can do this. So I'm going to take away those electrons on the carbon because I added a bond. So I'm still maintaining 8 electrons by removing those 2, because before that I had 10. Okay? Next I'll get rid of these electrons. How many electrons are on that second oxygen? 8. So I maintained the rule of 8, right? I kept 8 electrons, but I removed 2 electrons overall from the entire structure, because I shared electrons instead of just removing entire electrons. Okay, which you can't do, but this you can do. You can share them. So I still have 8 electrons on this carbon, right? 1, 2, 3, 4, 5, 6, 7, 8. Each line counts as how many electrons? 2. So I still have 8 electrons on the carbon. Do you see, Alejandro, how that's working? It doesn't. Okay? Because all we need to represent in the end is the exact number of electrons. I could have. It doesn't matter. But I'm not done. How many electrons are on my structure right now? 18. Right? I need how many? So what do I do? Good. So I add another bond. Okay? And I have to take away electrons from each thing that I added the bond to. Okay? So I have to take away electrons there and off of the carbon. Good. There we go. Okay? Yes? Okay, say it again, but a little louder, because I don't know if I really understood it. Like this? This has 20 total. Okay. I took away electrons. Okay? Okay. So I can't have 20 because when I counted the total valence electrons in my structure, I only have how many? 16. I have to get it to 16 electrons. This has 20. So any time that I need to remove electrons, the only way you can do it and maintain the rule of 8 is by making another bond. When I make a bond, I share 2 electrons and I remove electron pairs from each thing I bonded to. That reduces the total number of electrons in my structure by 2 because I removed 4 and I added 2 back as a bond. Now they're sharing those two, so they don't need two pairs. So that reduces my total number by 2. So I went from 20. When I made the first bond, I went to 18. When I made the second bond, I went to 16. Okay? So now that I'm at 16 electrons, this is my structure. I know it is because it maintains the rule of 8 and it has the correct number of valence electrons. It maintains the rule of 8 and it has the correct number. E minus, yeah. It's an electron. Okay, let's try another one. Okay? Let's try another one. Okay, this is the polyatomic ion carbonate. Let's draw its structure. This will be no more difficult than the one we just drew as long as you understand the process. Okay? As long as you understand the process. Okay. What is the first thing I need to do? Valence electrons. Carbon has 4. Oxygen. Who said 2? Somebody said 2 again. Okay. Oxygen has 6. Good. Times 3. Okay. What was it? 18. Good. 18. So how many valence electrons is that? 22 valence electrons. Now, this is a polyatomic ion. What charge does it have? What does that -2 mean? What does that mean about this compound? There's 2 more electrons. So, to my 22, I have to add 2 more because of the charge. It gained 2 electrons. So how many total electrons are in my structure? 24 electrons total. Okay? This is the total number of valence electrons in my structure. Yes? If it was, 2 plus, positive means it lost. Yes, you would lose, and we'll look at that. You subtract electrons. Good. All right. So I want to draw this structure. In these 24 valence electrons, I put carbon where? It is surrounded by 3 oxygens. How do I finish the first part of my structure here? Carbon needs 2 more. It needs a pair, 1 pair. Each oxygen needs 6. 3 lone pairs. It needs 3 lone pairs. Okay. I want to draw this structure. Right now it has how many valence electrons in it? 26, which is too many. Okay? It has too many. It has 26. I want 24. So if I want 24, I need to reduce the total number by, how do I do that? I make a bond from carbon to one of the oxygens. Okay? It doesn't matter which one you choose. When I make that bond, What else do I have to do? I have to remove a pair of electrons, or 2 electrons, from each thing that I bonded to. Okay? So I have to remove a pair off of the carbon. I need to erase. And I have to remove a pair off of the oxygen. Yes?
Is this the second stage of the bonding?
The second stage, is that what you said?
Yeah, like, those 2 lines, was there one line before? And
It was just one line before.
Yeah.
I added the second one, and then I removed electrons from here and here to maintain 8 electrons. Because I had 10 electrons before. I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had to remove a pair so that it would be 8. Now I have 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Everything still has 8.
By the time I lift my head on, I saw it, so I went out and
Okay, I removed them. Yeah. Okay. So, how many electrons do I have now? 24. That's how many I need, right? I need 24 valence electrons. So this is my structure. I know because it maintains the rule of 8 on everything. And there are 24 valence electrons in it. So it is my structure. Okay. Draw the structure of carbonite. Let's see it. Draw that structure. Okay, so essentially, carbon's in the middle, surrounded by 2 oxygens. You start everything out with 8. That's too many because you want 18 total electrons, right? So this has 20, so I have to remove electrons from here and here, and that's my structure. Okay? Now I have 18, I'm good to go. Okay? So this is the structure of this compound. Alright. So that's how I would draw these structures. So they're just going to go through carbon dioxide and carbonate. Okay. So we're going to write structures for the following. This first one, how many total electrons are in this structure? Oxygen has 6. Hydrogen has 1 each. So that's 8. Okay. So I need 8 electrons. So oxygen surrounded by hydrogen, surrounded by another hydrogen. Everything having 8 electrons. No, hydrogen can't have 8. It can only have 2 electrons because it doesn't have a P sub-energy level. So we can't put 6 more in there. It can only hold 2. All it has is an S. So hydrogen, when I make a bond, it's done. That's all it can hold. Okay? So, how many electrons are in that structure? 8. That's how many I want. I'm done. Okay? This is the structure of water. NH3, nitrogen surrounded by 3 hydrogens. Could I ever make a double bond on a hydrogen? Can't. So, what do you think? That's its structure. It is. It's very simple. We already drew that. Not sure why I put it there as an example where you draw when they gave it to you just a minute ago. Okay? NH4 positive. Let's try that one. NH4 plus. how many total electrons do I need in this structure? Nitrogen has how many? 5. Nitrogen has 5. Hydrogen, 4 times 4 has 4, right? Okay. I must have heard something else. Okay. How many total electrons are in the structure? 9 minus 1, 8. Right? That's a positive charge. That means I'm missing an electron. Right? So I have to subtract an electron. Literally. Okay, so that is my structure. Nitrogen with those 4 hydrogens. Nitrogen has 8. Each hydrogen has 2. Everybody's happy. Okay?
One question about that. If the nitrogen has 5 before you put the bond, you should put 9 elements, 5 elements, right?
No.
That is there. Nitrogen is just 5.
Has 5 valence electrons.
So when you dry it, you should put like 5, right? Outside.
No. Because after nitrogen undergoes a chemical reaction, it will fill its valence electrons. So when it becomes a compound, we know that it has 8 valence electrons on it. So we always draw everything with 8. Not with its original number, because this nitrogen has reacted with hydrogen. So it doesn't any longer have 5 valence. It contributed 5 overall to the entire structure, but it no longer has 5, it has 8. And each of these hydrogen no longer have 1, they have 2. Okay? So I draw everything as though it is full. 8 and 2. Okay? And that's how you start everything. Everything starts out with 8 if it's hydrogen 2. Okay, the other one was N2. How many electrons are in this structure? Total? How many? 10. 10 electrons. Because each nitrogen has 5. Nitrogen bonded to another nitrogen. I put 8 valence electrons on everything to start it out. Now how many electrons are in this structure? 14. 14 electrons. How many do I want? 10. So what do I need to do? Okay. I remove electrons from each nitrogen, right? Now I have 12. Make a triple bond. You are allowed to do that. Nitrogen is allowed to do that. That's what it does. That is the structure of nitrogen. Okay? In fact, if we look at that versus something like oxygen, O2, we need 12 electrons, right? I start oxygen out. It has 14, just like N2 did at the beginning. Now it has 12. So, this is O2. This is N2. Okay? The difference is that nitrogen has a triple bond, oxygen has a double bond. Well, that means oxygen's a little more reactive than nitrogen because it's easier to break a double bond than it is a triple bond. So if I'm burning something in air, then mostly what I'm doing is reacting it with oxygen, not nitrogen. Most everything, all the gas in the air that we breathe, is mostly nitrogen. And so, but it doesn't react as easily as oxygen, so when I burn something, it reacts with the oxygen, not the nitrogen. Because nitrogen has a triple bond. Okay. Single bond, you're confused now?
Oh, no, so like you said, green and nitrogen, I said, I always tell you to use oxygen.
Well, the air is full of lots of things, not just oxygen. It is mostly nitrogen. Oxygen is another major component, but it is not as concentrated as the nitrogen to produce oxygen. Yes, we need trees to produce oxygen. Yeah.
When you use like an air purifier, you know, like how, like is it like capable of like not certain things or
The air purifier takes out probably more things like bacterial and dust particles, those kind of things. But the gases, it's not going to purify those. They're too small for it to purify. And there's no way that it's going to purify the oxygen itself. Our bodies, though, do a wonderful job at that because they have these things called red blood cells that have hemoglobin, and oxygen is very attracted to hemoglobin and not nitrogen. So you breathe in all this air, and all that stuff like the nitrogen and the carbon dioxide that you get in there doesn't stay in there. It's only the oxygen that grabs onto the hemoglobin and transports to your cells in your body. You breathe out carbon dioxide, okay? Because you produce carbon dioxide in your body, and that gets released. And then the plants use it to make sugars and oxygen, and then we breathe it, and it's a big cycle. Okay? The circle of life. Okay, we won't sing that song. Okay, single bond, double bond, triple bond. Okay, triple bonds. 3 pairs of electrons are shared between 2 atoms. Very stable, just like I showed you. Nitrogen is more stable than oxygen. So if we burn something like our car that burns fuel, it mostly reacts with oxygen. Sometimes it gets hot enough to react with the nitrogen, and you produce some pretty noxious compounds. But luckily your catalytic converters grab that and try to purify it best they can. Okay? Alright. Now, the bond energy, so triple bonds, double bonds, single bonds, most energy to the least energy. Bond length, the single bond is the longest. And as I get to a double bond and a triple bond, it becomes shorter and shorter. So triple bonds are shorter than single bonds. And so single bonds are easier to break, whereas triple bonds, which are nice, close, and tight, are hard to break. Okay? We can't break them as easily. So compounds with triple bonds are not as reactive as something that would have a single bond or a double bond. Okay, resonance. So you know how we drew the structure for carbonates. And I said just choose an oxygen to make the bond on. You only made 1 bond on it, but there were 3 oxygens. Well, which oxygen do I choose? And the answer to that is you don't need to worry about choosing which one because all 3 of them are correct. Okay? Well, how do I know all 3 of them are correct? Because when there is a double bond like that on a structure, that double bond resonates, what it's called. It resonates throughout the entire structure. So it goes basically from one oxygen to the other. It resonates throughout it. Okay? The entire time simultaneously. You're saying, what the heck? That's voodoo. Yeah, it kind of is. Okay? These structures right here, none of these Lewis structures actually exist. They are a hybrid of all those. But the best way that we could draw it is to draw it with all 3 structures, and we're saying back and forth, it's resonating. But if you look at the actual structure of it, you would identify each oxygen to have the bond length of a double bond, even though you only have 1 single double bond in the entire structure. Okay? So that makes us understand that not any of these actually exist. It's a hybrid, And so resonance means that that double bond is existing throughout the entire structure on all the oxygens, okay, simultaneously. Okay, now we're going to talk a little bit about exceptions to the octet rule because, you know, chemistry wouldn't be any fun unless we had exceptions, and I try to confuse you more than what you're already confused with, okay? So, like I said, you should always draw everything with 8 electrons on it, but there are a few exceptions, okay? So, 90% of the time, the things you draw are going to you're going to follow the rule of 8. If there is an exception, I will mention it. This is an exception to the rule of 8 or something of that nature. Okay? But I don't want you to learn this as well as you learned the other thing. The other thing is what I want you to really understand. I want you to see this because this is truth. Alright? Some of these structures actually expand their octet and they can take on more electrons. If it's the central element, they can expand their octet and they can take on more electrons than 8. Okay, so that kind of goes against everything we've been talking about, you know, with the rule of 8. But this is how it works. Okay, okay, this guy's an exception because he has less electrons. Beryllium, and you look at beryllium and you say, well, he's a metal, he doesn't even form a covalent compound. Well, he actually forms one. That is with hydrogen. Beryllium with hydrogen, Be with 2 hydrogen. Beryllium has how many valence electrons? 2. He only has 2. So the only thing he can do is share those 2 electrons, right? So the most bonds he can make is 2. That's it. So all he can have around him, a total, when he makes those 2 bonds, is 4 electrons. He doesn't have 8. He's deficient in electrons to satisfy the rule of 8. Okay? So he can't. That's why he ends up like this. So beryllium, he is the first exception to the rule of 8 that I want you to understand. And it's only with, basically, with hydrogen. Nope. It won't form. That is the only metal that's really going to happen with. Okay? So the rest of the metals, don't worry about them. They don't form covalent compounds, only ionic. You're okay. It's just beryllium. It's the only one. Okay? Well, it has to do with electronegativity, but just realize that that's that one. Okay. Boron, this is the other one that you really need to know. Okay? Boron. How many valence electrons does he have? So how many bonds could he make total? Just 3 bonds. Okay? So if it was Be or BH3, he would make 3 bonds, and he can't have any more electrons on him. This is a common one that people mess up at. Okay? You'll see this on a test, and you're going to want to do this, which is, you know, wonderful that you want to do that, but it's wrong. Yeah. Mm-hmm.
So that, without those 2 that you did, it would still be 3 quote unquote instead of 6.
No, 6. He can only make 3 bonds.
Okay.
Because he only has 3 electrons, so he can only share 3 with somebody else to make 6 total electrons surrounding him. He can't have 8.
So it would just be 6. Oh.
Just 6 for boron. Okay. Number 5, boron. Those are the 2 exceptions. No, boron could be with chlorine, maybe. Boron, Cl, Cl, Cl. These guys would all need 8 around them because they would have to have a satisfied valence shell, but boron would only have 6. Okay? So those are the exceptions to the rule of 8. Okay? As far as deficiencies go. Because it only has, okay, boron has 1, 2, 3 valence electrons. So it can only share those 3. Once you get to carbon, I can make 4 bonds. Okay? But at boron, I can only make 3. So they only have 3 valence electrons. So I don't draw boron with 8 electrons on him because he can't do it.
So it's only those B.
B, E, and B. Okay? Those guys. Beryllium, boron. No. Because if I made 5 bonds, that'd be 10 electrons. So I can make 3 bonds, and then have, which is 6, and then have 2 extras to have 8. All right. Now,
You said we're not going to have many of those, right? Like, you want to-
you are not going to have many of those. Most of them will be what we just learned. Okay? This will be just like one question maybe or something. Okay? Expanded octet. This is where we take our octet and we expand it. So instead of having 8, we have 10 or 12 electrons on the central element. Okay? Why can I do that? Well, valence electrons are counted as S and P electrons, right? Okay, so there are some elements, once I get past fluorine and neon, I move into the 3rd energy level. So phosphorus, sulfur, chlorine, all those elements there, and below it, they also have a D sub-energy level. Okay? And they can take their valence electrons if they wanted to, and they could put them into the D and expand their octet. So now, if I was phosphorus, who has 5 valence electrons, right? Okay, phosphorus has 5, and instead of pairing one of those, it could spread them out into the D, and now it could make 5 bonds. Okay, do you see phosphorus here? How many bonds is he making? 5, which means he has how many valence electrons? 10. He expanded his octet into the D. Okay, so what do you think sulfur could do? It could make 6 bonds, right? Because it has 6 valence electrons. So it could spread all of its electrons out into the D, and then it would have how many valence electrons if it made 6 bonds? 12. Okay? To make 12. This is how I know if I have an expanded octet situation. You know how when you end up with 20 electrons and you need 18, you make a bond? Well, what if you end up with 20 electrons and you need 22? Then you need to expand your octet. Okay? That's pretty much how I know that I need to expand it. Okay? And essentially, if that's the situation, I need to add electrons. So where do I add them? I add them to the central element as a pair. So I had 20 in my structure. I needed 22, so I add electrons to the central element, make it 22. Okay? It's not really going to go past 12. Most of the time, it's not even that large. Sulfur is one of those that will do that, but chlorine doesn't make 7 bonds. Okay? Usually what chlorine does is it makes 4 bonds and then just has a bunch of lone pairs on it. Okay? That expand its octet past 8. So like 10 or 12 or something. Okay? So, but sulfur is one of the only ones that really goes to 6 All right. Now, how do I know the shape of a molecule after I've drawn it? That's what we're going to learn here. Okay? Be doesn't have any lone pairs on it, right? So these hydrogens, what they do is they spread as far away from each other as they can, which is in a straight line. So Be ends up being what we would say is linear, because they get away as far away as they can. Okay? This guy, boron, no lone pairs on boron, but there's 3 things bonded to him. Okay? So those three things spread out as far away as they can, 120 degrees away from each other, as far as they can, and they end up taking on a triangular shape. But it's a flat triangular shape. A flat triangular shape. Okay? So we say that it's trigonal planar. Trigonal planar. Four things. No lone pairs. 4 things. We're talking about the central element, by the way. That's the only thing we look at when we're trying to decide structure. The central element. 4 things. No lone pairs. It takes on a pyramid shape. Okay? And we say, just like this methane molecule here, CH4, okay, it takes on this pyramid shape. We say it's, we call it tetrahedral. It's a tetrahedron. Okay? We say it's tetrahedral. And you guys are probably all like, oh man, why are you telling me all this? In a minute, it's going to, it will be easy, okay? It takes on a very unique pattern that is not difficult to learn. Okay, now, NH3. Nitrogen, 3 hydrogens bonded to it. It has a lone pair on it. That lone pair is acting as if it was something there. So it takes on the pyramid shape as well. But we don't say it's tetrahedral. We say it's trigonal as well. Trigonal, pyramidal. It's a pyramid. I've never had anybody laugh at that. It is. It's trigonal, pyramidal. Okay? Trigonal, pyramidal. So right here, whenever we try to understand the shape of a molecule, we always look at the central element. Everything on the side doesn't matter as far as its shape goes. Okay? It's only what's in the middle. So if I look at the middle, and there are 2 bonds on it, and no lone pairs, see how this beryllium has no lone pairs? That means that the things that are bonded to beryllium here will spread themselves out away from each other as far as they can, which would be 180 degrees. 180 degrees, right? They have spread themselves out as far as they can, away from each other. So we say that this molecule is linear. It's just straight across, because there's no lone pairs forcing these hydrogens to move away or closer to each other or away farther away. Okay? So they're spread out 180 degrees. So you always look at the central element. That's how you decide the shape. So this one's linear. This one, no lone pairs, right, on the boron? Do we see any lone pairs on it? Good. So each of these fluorines, so there's 3 things bonded to this boron, and they will separate themselves as far apart away from each other as they can. So 120, 120, and 120. And the way this molecule ends up looking is like a triangle, and it's flat. So it's a flat triangle, so we say the name of it is trigonal planar. 3 things, no lone pairs. Okay? 3 bonds, No lone pairs. Trigonal plane. This one, the carbon right here in the middle, has 4 things protruding off of it. 4 hydrogens here. Okay? And it forms, from those 4 hydrogens, sorry, something just popped up on my screen. I have no idea. Okay, so from those hydrogens, you form the triangle shape in the front, but then you also in the back have another pyramid shape back here. So you form a pyramid, essentially. That's what you're doing. You're forming this pyramid from the 4 things protruding from that carbon. We say that's a tetrahedron shape, and we say it's tetrahedral. It has spaced its hydrogens completely away from each other perfectly. And that's the shape it ends up at. So, always. Because once I have 4 bonds, I've satisfied my octet, right? So I'm not going to have any other shape than tetrahedral. Because I can't put lone pairs on something that has 4 things on it already. Yeah, it can't. So this carbon, no lone pairs, right? Just has 4 hydrogens coming off of it. Has those 4 hydrogens. So it's very satisfied with that configuration. Yes? That it has to look like this? No. I could draw it like this. And just say it is it's tetrahedral. Okay? But I draw it this way and I just state that it's a tetrahedral molecule. Its shape is tetrahedral. Okay? So we don't end up drawing them in their shape for the most part. Okay? Alright. That's if I don't have any lone pairs. Well, what if I do have lone pairs? So here is the situation where I am bonded to 3 things, and I have a lone pair on the central element. Remember, we're only looking at the central element. We don't look at the other things when we're considering the shape. So that lone pair is acting as if I had a 4th thing bonded to me. It's taking up space. Okay? It's taking up room, so it ends up being that same pyramidal shape, just like the tetrahedral shape. Okay? But we don't say it's a tetrahedral. We say it's trigonal for 3, pyramidal. Trigonal, pyramidal. Okay? So, how do I identify it? 1 lone pair on the central element, 3 bonds. Trigonal, pyramidal. Two bonds, lone pairs on the central element, like water. H2O, oxygen has 2 lone pairs. The hydrogens are coming off of it. These lone pairs are acting as if they were actually things bonded. They're taking up space, they're taking room, so they're pushing those hydrogens away, and you end up with that same pyramid shape. But we don't say it's a pyramid this time. We just look at the shape of the hydrogens on the oxygen, and we say it's bent or angular. It's a bent shape. Okay? So that's the shape it takes. Bent. Okay. So, now that you're thoroughly confused, okay, Let's make it easier. It's easy, guys. 2 bonds. No lone pairs. 2 bonds. Lone pairs. Okay? If I am bonded to 2 things and I have no lone pairs, what shape am I? Linear. If I am bonded to 2 things and I have a lone pairs, 1 or 2, doesn't matter, I am bent. You're a bent shape. Okay? 3 bonds, no lone pairs. 3 bonds, lone pairs. If I have no lone pairs on the central element and I'm bonded to 3 things, what's my shape? Here. So for both of them, you can put trigonal as the first thing. If it's 3 things, right? Trigonal. Planar. The other one, with lone pairs, trigonal. Trigonal pyramidal. And anytime I have 4 bonds, I am what? You don't have lone pairs if you're 4 bonds. Okay? If you have an expanded octet, expanded octet, I'm not going to make you tell me the shape of it. Okay? So as far as 4 bonds go, it's tetrahedral if I'm asking for the shape. Okay? Sorry, you had a question.
No, I mean, you don't have a way, no lone pair because all are like...
Each one is 2, so that's 8 valence electrons around that central element. So it's done. It's satisfied. Okay? So 4 bonds, tetrahedral, before I even draw it. Okay? Before I even draw it, I know it's going to be tetrahedral. Okay? Alright. Pyramidal, because it had lone pairs on the central element, right? Bonded to 3 things, had lone pairs on the central element, it's trigonal pyramidal. Exactly. Okay? Alright. So that would be the central. And it's possible you could draw a structure with 4 things and lone pairs, but I would never ask you the shape of it. Okay? If it has an expanded octet, I will not ask you the shape of it. Okay? Alright. So here is just a chart kind of that whole thing. It makes it even more confusing than what I just showed you. Alright? But essentially you're bonded to 2 atoms. No non-bonding electron pairs, you don't have any, so no lone pairs. You're linear. This is just going to go over kind of what we just looked. Okay? 3 bonds, no lone pairs, trigonal planar. 2 bonds, 1 lone pair, angular or bent. 4 bonds, no lone pairs, tetrahedral. 3 bonds, 1 lone pair, trigonal pyramidal. 2 bonds, 2 lone pairs, angular. Okay? So just like we just talked about. I prefer bent, but you can call it angular if you want. Okay.
But for the test,
It will be multiple choice. So you don't have to tell me angular or bent, you just have to answer angular or bent, depending on the answer choice. Okay. Same thing. So let's determine the molecular geometry of these molecules. Okay? So PCl3, PCl, Cl, Cl. Okay, phosphorus, 5, CO3, 21, 26 electrons. If I have a molecule that is bonded to 3 things, and I put 8 valence electrons around everything, how many electrons do I start out with? 26. I said, anytime I have a molecule bonded to 3 things, and I start that structure out in its most basic form like this, okay, with only single bonds and electrons around everything, it will always have 26 electrons. You can't have 25. Oh, it will always have 26 electrons. Okay? So you don't even have to count them. If you put electrons around everything correctly, there's 26. So I need 26, but past 26 is this one structure. Yes. Anything with 3 bonds. Anything with 3 bonds is 26 in its most basic structure. This. I haven't done any double bonds, right? So if I did a double bond, that would reduce it to 2. By 2, so it's 24. But it always starts at 26. Anything with 4 will always be 32. That's 24. Okay? So I would know if it was 3 things and I had 24 electrons in my structure, I know that I would need to make a single bond or double bond somewhere and reduce it. Okay? But 3 things always starts out at 26. 4 things always starts out at 32. Okay? 2 things always starts out at 20. 20, 26, 32. Okay? So it's just a shortcut. If you're confused about that, then count the electrons. You don't have to try to memorize that. Okay? Just count the electrons. Yes. 20, 26, 32. 2, 3, 4. 20, 26, 32. Okay? Okay. Yeah, you're grabbing something out of the air. I'm not sure. Okay. Now, polarity. This is the easiest thing. I know, one more thing. No more, Mr. Crown. I can't think of another thing. Alright, polarity is so easy though. It is the easiest thing. Okay? If you drew your structure correctly, you will find it. Okay. Let me explain what polarity is, and then I will explain how easy it is to determine if your molecule is polar or not. Okay? So polarity is simply whether the molecule has partial charges or not. So remember when we talked about HF, and we said that fluorine is more electronegative than hydrogen. So fluorine pulls electrons towards itself, away from hydrogen. And that ends up meaning that the molecule of HF, which would look something like this, okay, this is partially negative and this is partially positive. Water. Water is a polar molecule. Okay? Water is polar because oxygen is more electronegative than hydrogen. So electrons get pulled towards the oxygen, leaving oxygen partially negative, hydrogen's partially positive. So water can dissolve a lot of things because it is polar. It has 2 polar ends to it, a negative pole and a positive pole. So it is a polar molecule. So how do I determine if something is polar after I draw its structure? Well, all I have to do is look for if there are lone pairs on the central element. Lone pairs on the central element. That makes it polar.
Even if it's just one, you want to share.
Even if it's just one. Because what that does is it disrupts the pull of electrons. So if water did not have lone pairs on the central element, if it was this, what shape would that be? Linear. So oxygen would pull electrons away from the hydrogen here and here with the same force. Okay? And essentially it would end up being that the electrons end up not moving at all because they're just getting shifted with the same force both ways. They can't move. Those electrons can't move. Here's a better example. A real molecule that's linear. We drew this one the other day. Carbon dioxide. Huh? It's nonpolar. Why? Well, it has all these electronegative oxygens on it, but the electrons are getting pulled this oxygen and towards this oxygen with the exact same force, so the electrons end up moving in no direction. They don't move because they're getting pulled this way and this way with the same force. It's like a tug-of-war with the exact same strength of members on both sides. Nobody's winning. That flag just stays right there in the middle. So the electrons don't move, so it doesn't become partially negative or partially positive. All the electrons stay put. Okay? And so this molecule is non-polar. The easiest way to identify that, are there lone pairs on this carbon? There are not lone pairs on the carbon. If there were, if this was more of like a bent shape and there's lone pairs on the carbon, then I disrupt the pull of those electrons. Now, this oxygen can pull electrons away from that carbon. And this oxygen can pull electrons away from that carbon. Because they're not situated perfectly apart from each other where the poles are exactly the same. Okay? So this situation would end up being polar. But that one doesn't exist. It's this one. This is carbon dioxide. And it is a non-polar molecule. Okay? Yes, we just said that. Yeah. You want me to go back a slide? Okay. I'm sorry? Okay, yeah, let's look at that. So if I was going to draw carbon dioxide, carbon has 4, O2 is 12, 16 electrons. If I started out in its most basic structure, carbon surrounded by 2 oxygens, right? How many electrons does it start out with? 20. I know I need to make 2 bonds because I have to reduce it to 16. The final structure is what I drew was 16 electrons. Okay, I skipped all the work to get there. But the starting point is always right here, 20. Okay. Okay. Let's determine whether the following bonds and molecules are polar. Okay? So there is a bond. This isn't showing the entire molecule. It's just saying there's a bond between silicon and chlorine here. So silicon, look at where it is on the periodic table. Look where chlorine is on the periodic table. Which one is more electronegative? Chlorine. So this would end up being a polar bond. The electrons would be drawn towards chlorine. It is a polar bond. Now that doesn't mean that a molecule of silicon and chlorine is polar, because actually it would be silicon tetrachloride would be the molecule. Are there going to be lone pairs on the silicon? No. So this molecule is actually what? Tetrahedral, and it is nonpolar. It is tetrahedral and it's nonpolar. So even though the silicon-chlorine bond is a polar bond, none of these chlorines wins out in the tug-of-war. They're all getting pulled with the exact same force. So nobody wins out, so it ends up being a nonpolar molecule. So just because it is a polar bond does not mean the molecule itself is polar. Okay? Just look at the central element. Look at the central, that's all I'm saying. Look at the central element, and that will tell you. Carbon and hydrogen, okay? Carbon is slightly, tiny bit more electronegative than hydrogen. So a very slight pull this way towards the carbon. Very little. Yeah, go ahead, plug your ears. You don't have to listen to me. So, just remember, no lone pairs on the central element. It's polar or not. Okay. This stuff is just more for your information. Nope. Because who is the most electronegative atom on the periodic table? Fluorine. The nonmetals are very electronegative. Okay? So within them, we have to decide which one's most electronegative. So fluorine is the most. As I move away from fluorine, electronegativity is decreasing. Okay? So actually the halogens end up being fairly electronegative, and as you move this way on the nonmetals, that is decreasing the electronegativity. Okay? But carbon ends up being much less electronegative than fluorine. Hydrogen is its electronegativity, if I brought it over here, would be more around carbon electronegativity. It would be close to. Not exactly the same. Okay? But carbon, there's no pull, right? They're exactly the same. They have the exact same pull, so this ends up being a non-polar. This one is slightly polar. This one is non-polar. Sulfur and chlorine is more electronegative than sulfur, so it's polar. So what do you think is going to happen if I bond a molecule to itself? Polar or non-polar? Non-polar because nobody can win out, right? So it's non-polar. Hydrogen bonded to a fluorine. Polar, because fluorine is more electronegative, it pulls it towards itself. Carbon, tetrahydride. Why? 4 things. It's tetrahedral. There are no lone pairs on the central element. It's going to be non-polar. Well, we've done water a few times. And it is polar because there are lone pairs on the central element. So I know it's polar. Okay? Oxygen is pulling electrons away from hydrogen. Okay. So that's how I would determine if something is polar or nonpolar by its shape. So when we look at the shape of molecules, it tells us, or after we draw it, we can determine its shape and whether it is polar or nonpolar. Okay? And from that, being able to understand whether it's polar or nonpolar is going to help us understand some of the characteristics of these molecules, like carbon dioxide. Was it polar or nonpolar? But let me draw it. Nonpolar. Carbon dioxide is nonpolar. Well, what is the physical state of carbon dioxide at room temperature? Is it a solid, liquid, or a gas? It is. It's a gas. What temperature would it have to be to become a solid? Anybody? Very, very, very. Have you ever heard of dry ice? Is that stuff pretty cold? It's pretty cold, right? You put that in your freezer, then everything in your freezer gets super hard. Don't do that. Okay? Because it freezes it really hard. Because dry ice is very cold. Okay? And so for carbon dioxide to exist as a solid, it has to be around negative 130 degrees Celsius. That's not Fahrenheit. I know you guys use Fahrenheit, so that's way different than Fahrenheit. Negative 130 degrees Celsius. That's cold stuff. Okay? Very cold. So, why is it that carbon dioxide is a gas at room temperature and water is a liquid at room temperature? Or something like some rubbing alcohol. Why is that a liquid at room temperature? Carbon dioxide is a gas. Well, it has to do with the fact that we have some things that are polar and some things that are non-polar. So if I have something that is polar, like water, then this part is partially negative, this part is partially positive, right? Well, what if another water molecule starts to come close to this water molecule? What do you think is going to happen? Yeah, see this partially negative part? It's going to attract what on the other water molecule? It's going to attract the hydrogen, which is positive, right? We're going to get an attraction between these two molecules. Those are called intermolecular forces. What happens if a carbon dioxide gas molecule comes close to another carbon dioxide gas molecule? Is there any sort of attraction there? No. Okay? Which I'm going to tell you there is in a little bit, but a slight one. Nothing like these polar ones. Okay? But the idea is that these guys are not attracted to each other. These guys are. They're holding on to each other. So if this water molecule wants to escape and become a gas, it has to overcome this attraction to do so, which holds it in the liquid state. You can't escape. I'm not letting you. They're holding on to each other. Whereas the carbon dioxide molecules, they can just escape. Well, a lot of solids are ionic things, ionic substances. A lot of liquids at room temperature would be things that are polar. Absolutely. Because that's what's holding them in that phase at room temperature. A lot of things that are gases, some things that are gases at room temperature can still be polar, okay? But they just have weaker attractions than these polar molecules, like water. And then once you get to non-polar things, they have very low, what we call boiling points, that allow them to go from the liquid to the gas state. It has to be very cold to keep them. Have you ever heard of liquid oxygen? Liquid oxygen is very, 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 very cold. Liquid hydrogen, very cold. Very, very cold. Because to keep them in the liquid state, they are nonpolar molecules, right? Because it's H2 and O2. They're nonpolar molecules. They're just bonded to themselves. And to keep them in a liquid state, I have to get them super cool. I have to super cool them down to ridiculously cold temperature. Okay? And then they will exist as liquid hydrogen and liquid oxygen. Liquid nitrogen, N2. Have you ever heard of that? So if you've ever worked in the healthcare industry or something, then you might see these little things, they call them dewars, and they roll them around, and there's liquid nitrogen in them. What are they using that for? They're using it to cryogenically freeze living things. Bugs. Okay? I did it all the time. Take a bug, grow it up on a petri dish, okay, and then you collect some of it. You put it in a solution of glycerol, which doesn't freeze in a crystalline way like water does, that would burst the cells open. So you put it in the liquid nitrogen, and it flash freezes them. Immediately, they're frozen. A year later, take them out of the freezer, or the liquid nitrogen, take them out, put them on a plate, a petri dish, there they are, frozen. They're as happy as can be. I don't know, they don't really have feelings, but. Oh yeah, those things, you can keep them there indefinitely, frozen in that place. Well, no, I'm not talking about eukaryotic bugs like a grasshopper or something like that. Okay, I don't know if you can do it with that. I'm talking about bacteria and prokaryotic bugs. Okay, the microscopic things. Okay, that you grow up on petri dishes. But theoretically, you can do that with a grasshopper or something, or even a human. Yeah, you haven't heard of them trying to cryogenically freeze people? I don't know. I have never tried it. What's that? Just bacteria. That's right. Those are bugs. You don't want those things getting in your lungs, right? Okay? Alright, so, but that's what it's used to. It cryogenically, it's so cold that it flash freezes it. Flash freezes them. Okay? And they're frozen. And you can leave them there indefinitely. And then later grow them up. It freezes things so quickly that you skip all those like harmful effects. That's the idea. Because if I just stuck bacteria in a freezer, they would die. They'd be dead when I pulled them out. You can't do that. You have to flash freeze them so that they're frozen in an instant, as soon as you put them in there. Which would happen to a human individual if you put them into liquid nitrogen. They would flash freeze. Now, but your body is so full of water, that could be difficult because it will still form ice crystals that could burst your cells. And that's what we have to look out for with bacteria. We can't freeze them in water because it might. So that might be a difficulty with flash freezing human individuals. I have no idea. Yeah, they'll freeze off the. Yeah. Mm-hmm. They do. They'll just, even if you use those wart removers, spray it on your skin, something like that. You have to be, yeah. So, anyways. So, carbon dioxide is very cold, dry ice. Liquid nitrogen, very cold, because they are nonpolar. So they exist in that state at very low temperatures because they can't exist as a liquid in any higher temperatures. They'll just, their intermolecular forces don't attract in such a way to hold them together. They'll just go to the gas phase. Okay? And in fact, dry ice, if you put it on a table, it doesn't melt. It just evaporates because it goes straight from solid to gas phase. Completely. It doesn't even ever go into the liquid phase. At the temperatures that or the pressures in room pressure, basically atmospheric pressure, it won't. If you increase the pressure of this room high enough to like 5 atmospheres, then it would melt into liquid, and then it would go into the gas phase. Okay? From carbon dioxide? Too much carbon dioxide. Oh, sure. If your atmosphere is saturated with carbon dioxide, that you're breathing carbon dioxide too heavily, you will suffocate, right? Because there's not enough oxygen then in that situation for it to sustain you. Yeah, they could suffocate. Just like the astronauts, they have to scrub out all the carbon dioxide in the space shuttle because otherwise they breathe out carbon dioxide. So eventually it builds up, and they have these scrubbers that pull it out. So if you've ever seen Apollo 13 movie, that was one of the issues. Okay. So, solubility. This also deals with polar and nonpolar. So if something is soluble in another thing, meaning it dissolves in that other thing, okay, If something is soluble in another thing, then it is because they are of the same polarity. That they are either polar or they are not. Okay? So, for example, water will dissolve sugar. Sugar is a polar molecule. It will dissolve sugar. Okay? Or it will dissolve rubbing alcohol, which is also polar. Okay? Those two things will mix in each other, and they will become one substance. Okay? Now, will water dissolve oil? No. So oil is fat, right? It's like these big, long carbon, hydrogen, non-polar molecules. And the reason they're liquids and are solids at room temperature is because they're super big molecules. All right? Not like a nitrogen and a hydrogen molecule that are non-polar. These are long polar molecules, fatty molecules. Okay? They don't dissolve in water because those molecules are non-polar. Oils and grease and fat, they are non-polar molecules. And so they won't, of something dissolving into another thing that's non-polar. Well, if you wanted to dissolve oil into something, so vegetable oil, you could dissolve it into something like gasoline, because those two things are non-polar molecules. Bleach would be polar, so it will dissolve in water. Okay, every solution that you know of would be soluble in water because it's already in water. Bleach, it's like a percentage of bleach, right? The rest of it's water. What's that? No, they will not mix because it's a water solution. Bleach is a water solution. Now, if you've ever tried to take your baking powder, your chocolate, not baking powder, but your baking cocoa, it dissolves better in the oil than it will into the water. So if you wanted to mix it first into the oil, it'll actually make a smoother solution rather than trying to mix it into water first. Because well, you look at how well it does. Well, and that's another situation where, well, what about things that have both polar and non-polar parts? They can dissolve into both things. And that's actually like soap. Okay? So if I can't dissolve the greasy thing off my plate into the water, how am I going to wash my plate?
Warm water.
Okay, warm water will just kind of melt it. Doesn't really mix it though, right? So how do I get rid of the grease? I use soap, Dawn, or whatever. Okay? Because soap has both polar parts to it and non-polar parts to it. So the non-polar parts dissolve the grease, they surround the grease particles and make it so that all the non-polar parts are interacting with the grease, and on the outside of that now is a polar bubble that can then get dissolved into the water. What is it made? Oh, it would be a combination of compounds, but I don't know exactly. But it would, probably the non-polar parts would have carbon, hydrogen into it, and then the non-polar parts, or the polar parts, would probably have oxygen in it. That's a very common. So, another example of that, in our cells, you have things called membranes, cellular membranes. Okay? So your cell membranes are what we call a bilayer, a lipid bilayer, phospholipid bilayer. Yeah, because they have a polar phosphorus head, phosphate head. What's phosphate? PO4, right? So they have these phosphate polar heads, and then they have these long fatty acid molecules that are nonpolar. Okay? So it's a phospholipid. Lipids are the fatty acid, nonpolar things. Okay? So it's a phospholipid bilayer. Why is it a bilayer? Because you have the polar heads on the outside and the inside of the cell. So just kind of really quickly. So these would be where the polar heads are around. And they are up here. And then they have these lipid tails that go inside and interact with all the lipids from the membrane, the other part of the membrane. This is a cellular membrane. Okay? On every single of your cells, you have a phospholipid bilayer. The nonpolar tails are interacting with the nonpolar tails of the other phospholipid. One phospholipid here, one here. They interact with each other because they love each other. Okay? Well, the phosphate heads, love water. And what do I have inside the cell? Water. These guys hate water. They're hydrophobic. They're afraid of it. So they run away from it and they turn this way, away from water. Well, if there wasn't another phospholipid right here to interact with, then they would be interacting with water. They'd be all confused. Okay? So I have water on the outside, water on the inside. These are like dissolving light. They're interacting with each other. Nonpolar interaction. Water is polar. The phospholipid head is polar. They are interacting. Okay? And we create a cellular membrane. You create a cellular membrane. And now I have separated the outside of the cell from the inside of the cell. I can package my DNA even in another cellular membrane in the nucleus. Okay? Another phospholipid bilayer in the nucleus. And I can control passage of stuff. I can decide what comes in and out of my cell because I have separated those components. So, getting inside of a cell is a difficult task because a lot of these molecules come and they have to bind to receptors and things to go in. But there are hormones that are cholesterol hormones, and cholesterol is a nonpolar molecule, and guess what it does when it comes to a cell membrane? Right through it. And then it goes straight to your nucleus and turns something on. It says make this. So those cholesterol hormones just pass right through because they are nonpolar. They can just go right through the cell membrane. No, nothing is stopping them. Okay? And it's all based off of that idea of polar, nonpolar interaction. Okay, so there is another type of interaction, intermolecular interaction, okay, that is very strong. It is called hydrogen bonding. Hydrogen bonding occurs between molecules that are bonded to, between hydrogen molecules and the other molecule it's bonded to, if it is oxygen, nitrogen, or fluorine. Okay? It cannot be sulfur. Sulfur dioxide does not hydrogen bond. Okay? It will not hydrogen bond. Because it is not electronegative enough. Oxygen is electronegative enough that it will hydrogen bond. It creates enough polarity in the molecule between the hydrogen and the oxygen that they will create another type of interaction called hydrogen bonding that will allow them to interact in a stronger manner. So water, even though it's a really small molecule, H2O, has high boiling point and melting point because of its hydrogen bonding. Okay? So sulfur dihydride, sulfur SH2, should boil and melt at a higher temperature than H2O. Okay? But it doesn't because oxygen has hydrogen bonding. Because the boiling and melting points are also dependent on the weight. H2S is heavier than H2O. And so it should have a higher boiling and melting point. But it doesn't because oxygen-hydrogen bond. Hydrogen bond. Okay? So, the only molecules that hydrogen bond, oxygen, nitrogen, and fluorine. Those are the only ones. So if I take NH3 and H2O, put them together, you will see hydrogen bonding. Hydrogen bonds also occur between the water molecules themselves. Okay? And that's what gives them strength, like surface tension strength. Those little skeeter bugs that run across water, they use that surface tension of the water that's created from hydrogen bonding to be able to do that. You can break the hydrogen bond using a soap, a surfactant. You put soap in there, the hydrogen bond would break apart where the soap is, and that little bug would run across and fall right in because there's no more surface tension where the soap is, because you disrupted the hydrogen bonding in the moment. Okay, it's a neat little trick. No, they can't, because you've broken. Yeah. Okay. We got a bug hater in here. Yes. Oxygen, nitrogen, and fluorine. Those are the only three. The most electronegative atoms. Those three electronegative atoms will hydrogen bond. Okay? Nothing else will. Right. Okay, so we've talked about polarity. Polarity only occurs on covalent molecules because they have structure to them. Ionic compounds don't have polarity. They actually have actual positive and actual negative characters to them. They conduct electricity, okay, because they have positive and negative characters. Covalent molecules won't conduct electricity. So if I take table salt and I dissolve it in water, that will conduct electricity. I can light up a light bulb through the water if I wanted to. Okay? But if I take a sugar molecule, which is a polar covalent molecule, and I dissolve it in water, and then I try to conduct electricity through it, nothing happens. Okay? What's that? What? Okay. Eat it with bread after you dissolve. There you go. But it will not conduct electricity. Okay? Water itself is a covalent polar molecule that does not conduct electricity. That is a misconception people have. Water does not conduct electricity. If I have pure water, it will not conduct electricity. Absolutely. Deionized or distilled water, purified water, does not conduct electricity because what have I taken out of the water? Why did I have to purify it in the first place? Metals, ions, right? What's in our water? All kinds of stuff. Yeah, they put probably some fluoride in there, or they put, which is an ion, right? F minus, fluoride. They put that ion in the water because it strengthens your teeth or whatever. Okay? So that's what's conducting the electricity. All the ions and the minerals, which are ionic compounds. All the minerals, the salts in your water, those are ionic compounds. That's why if I drop my toaster in my bathtub, I'm toast. Because of all the minerals. Okay? And which is why a lot of people have to buy a water softener. Because of all the hard water. All the minerals that are in their water. Me too. Destroys everything in your house. Yep. So that's what's conducting electricity, not the water itself. Pure water will not conduct electricity. Okay? So now if we look at these properties of ionic covalence, Okay, the physical state of an ionic compound, they are usually solids at room temperature. Okay, covalent compounds can be solids, liquids, or gases. They could be any of them. Melting and boiling points. These are astounding. The melting point is at the temperature at which a solid is converted to a liquid for ionic, and the boiling points for ionic is tremendously high. Very, 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 very high. Okay, we'll look at that. Versus covalents, which are not nearly the same. Ionic compounds have much higher melting points and boiling points than covalent compounds, because a large amount of energy is required to break the electrostatic attraction. So those positive, negative attractions, I would have to put in a lot of energy to cause them to melt. Okay? In other words, it's melting an ionic compound is almost like thinking of, well, it is. It's like molten rock. Okay? So rocks are ionic minerals, right? To melt those things, you'd have to have super high temperatures to make them molten. Okay? So it doesn't happen very easily. Ionic compounds are crystals. Covalent compounds can be crystals or amorphous, or they, meaning they don't have a regular shape. Okay? Ionic compounds dissolve in water. That's where they'll dissociate. That's when they conduct electricity, when they dissociate. If they're together, they won't. So if I tried to conduct electricity through solid salt, table salt in my kitchen, it won't work. But as soon as I dissolve it in water, I can conduct electricity through it very well. Okay? But before that, I couldn't. That's when they become electrolytes. We've heard about that, right? Electrolytes in our Gatorade. Potassium, K+, the potassium ion, calcium ions. Those are the electrolytes that they put in there. Okay? Probably some chlorine ions. You need those things. The reason they do that is because you need those in your body. Your body uses electrolytes all the time. Yeah, your body conducts electricity. So if I touch the tip of this pen, my brain registers that. It says, hey, you're touching the tip of that. I can feel it. Well, it's not actually my finger that feels it. What feels it? My brain feels it. My brain is telling me that I feel something. How did I get that sensation from here all the way here? Through an electrical impulse that is conducted through my neurons, right? Through potassium, through the potassium. What is it? Calcium, potassium. Through the pump, the calcium potassium pump signal that occurs. Okay, so you're conducting ions across the membrane, which changes the electrical potential and causes a signal to be sent. And it's that fast. Super fast. Okay? And that's, so your body needs those electrolytes. Muscle contraction uses a lot of calcium. So you need electrolytes for your muscles. Covalent solids usually do not dissociate and do not conduct electricity. They are non-electrolytes. Just like water, sugar, those things are non-electrolytes. They are covalent compounds. They don't conduct electricity. Okay, comparison of ionic versus covalent compounds. So, ionic, metal and non-metal. That's how I identify it. The electrons are transferred completely. Physical state, solid or crystalline state. They dissociate into electrolytes, and they have high melting and boiling points. Covalent compounds, two nonmetals. So you would almost think there would be more ionic compounds than covalent compounds because there's more metals on the periodic table, but that's not true because a lot of the metals can only associate with the nonmetal in only one ratio. Whereas covalent compounds, each element can combine in multiple ratios. It's not hundreds of ratios. Okay? So there are more non-metal covalent things than there are ionic things, even though there's less nonmetals on the periodic table. Think about your bodies. Your bodies are organic material composed a lot of carbon, hydrogens, and oxygen. And every single molecule in your body that has those carbons, hydrogens, and oxygens in it, those are covalent compounds, but there's thousands of different compounds with carbon, hydrogen, and oxygen in your body. Okay? So that's an astounding amount of compounds that you can create from those nonmetals versus the ionic compounds, which there's not quite as many. Okay? Covalent compounds, we share electrons. Physical states, you can have crystals or amorphous. So one example of a very strong crystal that's covalent would be a carbon diamond. Okay? That would be one that you would consider to have a high boiling and melting point, okay, and which would be a crystal. So a lot of those crystals are covalent molecules. They have strong, high boiling and melting. But then you have a lot of other things that would be amorphous. So, for example, silicon dioxide, it will be a crystal. In its crystal state, it's a crystal, but it's not a clear crystal. If you make it amorphous, an amorphous crystal of silicon dioxide, it becomes clear. And that's what we use as our glass on our windows. Is that amorphous substance of silicon dioxide. Because we have made it amorphous, it has now become clear crystal. But otherwise it would not be clear. Okay. Covalent compounds do not dissociate or come apart when you dissolve them in water. So if I dissolve a covalent thing in water, it does not create electrolytes. It stays together as one entire thing. Boiling and melting points, for the most part, are low, but if you have those crystalline like structures like diamonds and things of that nature, they would be high, very high. Okay. So to melt or boil something, I have to overcome the intermolecular attraction, those forces that are holding them together. So if I want water to boil, I have to heat it up, right? And that allows it to break its hydrogen bonding and escape. Because those water molecules are holding on to each other tightly, so if I add enough energy, it'll allow them to escape, and they will boil away. Same thing with melting. They're solid together, stuck together. I add enough energy, and they melt, and they start to roll over each other instead of being stuck in one position. And then they become a liquid. They're rolling over each other. Okay? So, what affects melting and boiling points? Molecular mass and polarity. Okay? Polarity and molecular mass will affect whether what your boiling and melting point is. Okay? Now these are predictive methods of boiling and melting point. So it doesn't mean that you go and you look up the actual melting and boiling point that is contradicting what you learned. Okay? No, because there's other factors that might come into play. But this is just a general predictive way to understand the boiling and melting points of these molecules. So here's some examples, though, before we get into it. Nitrogen has a melting point of negative 210 degrees Celsius, right? Like we said. Liquid nitrogen is very, very, very cold. Okay? It has a boiling point of negative 196 degrees Celsius. So you put something in there at those temperatures, somewhere between negative 210 and negative 196, and it's going to flash freeze. Very cold. Okay? Here's oxygen. Ammonia, negative 78, negative 33. Water. Water jumped up all the way to 0 and 100. Okay? Very high melting and boiling points for this small of a substance. And that has to do with hydrogen bonds. Sodium chloride, now listen to this, this is ridiculous. Okay? Melting point, 801 degrees Celsius. Boiling point, 1,413 degrees Celsius. So if you take the sodium chloride, put it in a pan at your house, you're not going to be able to melt it. It's going to sit there and laugh at you. Okay? But if you put some sugar, sucrose, from your cupboard in there, it's going to melt. Alright? You put it in the pan on your stove. It will melt. When we are considering the boiling points of liquids and melting points of solids, okay, they are determined by whether and this is for covalent compounds, because if it is an ionic compound, that is going to go right to the top of the list. Okay, so if you have a list and you identify one of them as ionic, you know that one has the highest melting and boiling point. It goes to the top. Okay, straight up there. Now, after that, you need to identify whether the covalent compound is polar or nonpolar. How do I do that? How do I know if it's polar or nonpolar? Good. If there are lone pairs, so you have to draw the structure. Okay? So I have to draw the structure to be able to identify whether it is polar or nonpolar. This molecule is polar or nonpolar? It is polar. That is a polar molecule. So I have to draw it, then identify whether it is polar or nonpolar. Once I know whether it is polar or nonpolar, I will be able to identify or predict which has a higher or lower boiling point. Okay? And the way that I do that is first knowing whether it's polar, and then by its molecular mass. Heavier things have higher boiling points. If it's heavier, it has a higher boiling point or melting point. Boiling and melting points are essentially synonymous. They're gonna follow the exact same trend. Okay? So if it's heavier, the larger the molecule, higher melting and boiling point. Okay? So this is how you will arrange them. If you have a list of things like, let's see, we just did this one. Okay, I want to arrange this. Actually, let me throw one more in there. I want to arrange this according to its boiling or melting point. Okay, this list. How am I going to do that? I need to identify what first? Polar. Okay, so I would. So let's throw an ionic in there. Okay, I identified this as ionic. Where does that go on the list? The highest. It's just you only have one ionic. You're not going to be given 3 ionics and have to arrange them. You're not going to have to do that. Okay, if there's an ionic on your list, throw it to the top. It's the highest melting or boiling point. Okay, so that one's ionic. It's going to go to the top. What is the next thing I need to identify? The rest of them are covalent. Polar or nonpolar. Good. So, of these, which ones are polar? Okay, well we drew this one earlier, just a minute ago, and it was what? Polar. Okay, so it is polar. Carbon dioxide. We've drawn that a few times. Anyone remember what it is? No? Nonpolar. That's right. No lone pairs. So it's nonpolar. Okay? It's a linear molecule. Those oxygens are pulling with the exact same force. Nobody's winning the tug of war for electrons. Okay? So it is nonpolar. Okay. What about N2? I don't have to draw that to know if it's polar or nonpolar. What is it? How do I know? They're the exact same thing. If you have a nitrogen bonded to another nitrogen, who wins the tug of war? Nobody. It's a diatomic molecule, so it is nonpolar. Next one is also nonpolar. Carbon tetrachloride. How many things is carbon bonded to?
4, never mind.
Do I have any lone pairs if I'm bonded to 4 things?
Not possible.
Not possible, so I am nonpolar. Okay? What about SO2? Has 18 valence electrons. If I started out, there's 20, so I have to make what? I have to make a single bond to bring it from 20 to 18. That means, do I have lone pairs? I had 2 pairs of lone pairs on the central element. I removed one of them. I still have 1. So this is polar. Okay. Now, what is the next thing I have to do in order to identify which has the highest to lowest, to arrange these from highest to lowest predictively according to their boiling or melting point? Okay. Before I do that, I need to put them into their respective places. Okay? So these are the polars, right? Polar molecules have higher melting or boiling points, so they're already above the nonpolars. Polar things have higher melting and boiling points, so they go above the nonpolars. So within the polar group, now I need to look at their mass. Which of those has the largest mass? So to determine the mass, I need to look at chlorine. It has a mass of 35.5. Okay, I have 3 of them. So I would calculate the mass of the chlorine. 35.5 times 3, 106, plus the phosphorus, which is another 31. So phosphorus weighs 100, or PCl3, phosphorus trichloride, is 137.5 mass. Okay? Does everybody see how I did that? No? Okay. How many chlorines are in that molecule?
3.
How much does chlorine weigh on the periodic table? 35.5. Or you could, around 35, probably wouldn't make a big difference if you just said 35. Okay? So I multiply 35.5 times 3. And then I add the mass of a phosphorus. 1 phosphorus, which is 31. That mass is 137.5. Okay? So that's how much PCl3 weighs. SO2. Oxygen weighs 16. Sulfur weighs 32. So 16 times 2 plus 32. And it has a mass of 64. So, which one has in the polar group, which one has the higher boiling point? Okay. So I'm going to start with my list with sodium chloride, and then phosphorus trichloride, and then what? Good. Sulfur dioxide. Okay? So my list, this is how I'm starting my list. Now, I have to arrange this group, which is the nonpolar group. Which one goes to the top? Okay, you have to determine their masses. Without even, calculating all the masses, which one's going to be the heaviest? This one has 4 chlorines. Chlorine's one of the heaviest elements out of everything here, right? And there's 4 of them. That one's going to go to the top. So the next one is CCO4. Okay, carbon tetrachloride. Then which one? Carbon dioxide. Now which one? N2 and then H2. That's how I'm going to arrange my molecules. Okay? So, predictively, I would say sodium chloride has the highest boiling point, and then PCl3, then SO2, CCO4, CO2, N2, and then H2. You won't be given 2 ionics. If anything, you'll just be given 1. And you'll just put it right to the top. Okay? Covalent bonds? Yeah, because ionics, they actually steal electrons. So you can't have polarity. Ionic bonds already have polarity, essentially. You have a positive cation and a negative anion. So we don't say they're polar because basically everything about them is polar. But we do say that these, and also in that regard, they also cancel each other out when they come together. Okay, so even though they do have separate electrons, they don't actually have a charge once they're together. Whereas here, these polar guys, they do have partial charges. They don't cancel each other out necessarily, completely. Okay? All right. So that's how you will do the predictive method for these. Now, if you look it up online, you might even discover that this one has a higher boiling point than this one. Okay? So if you did that, you would arrange it incorrectly for what it's asking you. Saying this is a predictive method. Okay? Carbon tetrachloride may be a liquid at room temperature, and SO2 may be a gas. So it's not saying that this is absolute truth. It's just a predictive method. Okay? You understand that? So don't go online and look up individually the individual melting and boiling points to be able to arrange this, because you might get it wrong. It's asking you to predict them, to arrange them in a predictive way, okay, according to the how they might be. All right, and the way that works is ionics first. So like this, ionic, then polar, then nonpolar. Okay, now within this polar group, there's actually one other thing we have to consider that we didn't consider in this last example. So what if I had put water in the mix? Where would it go? Where would I insert it? Is it polar or nonpolar? Okay, it's polar, so it goes in this group, right? It's polar. Where does it go in that group? Okay, so water is lighter than both of these. So where does it go? So it goes below it. Well, we're missing one consideration. Water also does what? Not only is it polar, but it has what we call hydrogen bonding. You remember hydrogen bonding? Hydrogen bonding. What three elements hydrogen bond? And oxygen. Yeah. Fluorine, nitrogen, and oxygen. They're right next to each other. Okay? So if you have a fluorine, an oxygen, or a nitrogen bonded to a hydrogen, then it hydrogen bonds. Does this hydrogen bond?
No.
No. This doesn't hydrogen bond. There is no hydrogen on it to hydrogen bond with, right? So this does not hydrogen bond. So I need a hydrogen. So water, because it hydrogen bonds, actually goes right under sodium chloride. Okay? Because of the hydrogen bonding, so when I'm writing here, ionic polar, I'm going to write right here, hydrogen bonding. Right above the polars. And then I will arrange them according to mass. I did. I'm sorry? We're just reviewing how we would do it. High mass to low mass.
What happens if you get more than the hydrogen bond? Then you see later.
You probably won't have that situation, but no. I think so. It might work. It might work that way still. Yeah. High mass, it might still work. Because basically you'll have NH3, H2O, or HF. But then it gets a little trickier when you get other molecules that hydrogen bond, which are large organic molecules. But you won't have to worry about those. But essentially you probably won't be given two. You'll probably be given one, and then you'll have to just put it at the top of the polar group. Okay? Okay. Is this making sense? Is everybody following it okay? Okay, so in the polar group, I have to put the one with the higher mass at the top of that group and arrange them from high to low mass. And that's how their boiling points will arrange. Okay? And then in the non-polar group, which is right below the polars, I do the same thing, high to low mass. Okay? And that's how we got that earlier set. All right, let's see. So this is a great look at what's happening with these ionics. Okay? So here we have some polar covalent molecules. All right? These actually are hydrogen bonding ones, so it doesn't really give us a good glimpse at polar molecule melting and boiling points. Okay, but you can see the nonpolars have much lower melting and boiling points. And then you get into the polar groups. The ones that hydrogen bond, especially like water, jump way up there, right? But then you get to these ionic compounds, and it's ridiculous, right? I mean, melting point for water is 0 degrees Celsius. For sodium chloride, 801 degrees Celsius. All right, you're not going to be able to go home, dump some sodium chloride in your pan on your stove, and melt it. It's not going to work. You're going to sit there all day, and it's going to laugh at you. You cannot. Good luck. Go ahead, try it. But you could take some sugar, a covalent compound, dump it in your pan, and what's it going to do? It's going to melt and begin to burn eventually, right? It's going to melt, all right? You'll caramelize it eventually, and then it might burn after that. But it will melt, yeah. Well, actually, that's something we're going to learn about. We're going to learn about that colligative property of how you mess with the boiling points of water by adding something to it, like salt. And that will increase the temperature at which water boils. And we'll learn about that later in chapter 6, 13. We won't get to chapter 13 of this class. But I think it's around chapter 6 that we'll learn about that. Okay? All right. So, potassium bromide, another, these are ionic compounds. So you just put them right to the top of the list. They just go because, it's so extreme, it's just going to be right up there. nothing to even think about.